Here we are at example 7 from our 3.37 notes. We're asked to graph the system of linear inequalities, and in this case we also have an absolute value inequality, and then find those vertices. So we're just going to go ahead and label this first one as a red line so that distinguishes the shading for in a little bit. And we're going to start out by writing out the vertex for this absolute value function. So our vertex is, just taking the opposite of this, comes out to be 1, taking our k value just as he is, -3. So it looks like at 1, -3, we would see our vertex. Now from that, looking at the slopes, well, we notice that our number on the outside of our absolute value is a 1, and the number right in front of x is 1. And to find the slopes, we just multiply these two numbers together. So it looks like it's going to come out to be 1. And then also -1, just taking the opposite of that. Now, from that vertex, we should see a V opening upwards because our A value is positive here. So we should have a V with a slope of 1 and -1, but it's opening upwards. So something like this. Also recognizing that it is in fact a solid line because we have that bar underneath indicating a solid line, we should see an image that does something like this. Now we have to go ahead and test to see which way we need to shade. So we can go ahead and test a point like 0, 0. We see that 0, 0 is clearly within side of our V, but we need to see if that's the area where we're going to shade or if we're going to shade underneath it. So is 0 larger than or equal to 0 minus 1 minus 3? So 0, is that larger than or equal to, looks like 0 minus 1 is -1 in the absolute value, minus 3. The absolute value of -1 comes out to be +1 minus 3. So 1 minus 3 comes out to be -2. Is 0 larger than or equal to -2? It most certainly is. So we tried this guy, he worked. That means then that any of these other points would also work. Now moving on to our green line. We see that he's in standard form, so we're going to go ahead and graph this using standard form. Creating our box, throwing in 0, 0 on that main diagonal and an x and a y above them. Now going ahead and throwing in 0 for x. Essentially this piece is gone, so 2 times what gives us 4? 2 would accomplish that. Throwing in 0 for y, essentially this piece is gone. X then would have to be equal to 4. And in doing so, we've actually created our y-intercept and our x-intercept. Plotting those now, we have 0, 2, and 4, 0. Now, just looking to see if this is a solid or a dotted line, we notice that we have this bar underneath, and that's going to basically say that we have a solid line here. So connecting these 2 points, we end up with a solid line. Now we have to go ahead and test to see which area we're going to shade. So we'll go ahead and test the origin 0, 0, which is below our line. Is 0 plus 2 times 0 less than or equal to 4? Well, on the left side, we just end up with 0. Is that less than or equal to 4? It most certainly is. So we tried 0, 0, he worked. That means that any one of these guys underneath would work as well. Lastly is going to come our blue line. X is larger than or equal to -4. Well, here's our x-axis. We're going to go ahead and go -4 on that axis. So -1, 2, 3, 4, place of dot there. There's no y value. So y value could literally be anything, just as long as x is -4. So you should see a vertical line here. Now, just checking to see if this is a solid or dotted, we see that bar underneath, which means that we have a solid line here. So again, y could be anything, as long as x is -4. Here is our vertical solid line. Now we have to go ahead and check to see which way do we need to shade. Well, we can test a point 0, 0, which is clearly to the right of that vertical line. So we'll test 0, 0. Is 0 larger than or equal to -4? It absolutely is. We tried him, he worked. That means all of these other guys would work as well. So in just looking at our final shaded region, it appears that it would be this kind of, looks almost actually like a, kind of like a trapezoid. Right. But that would be the region where that they are all inclusive. Now looking at the vertices, we see that we have a vertex happening right here, and that is, looks like -1, -3, coming from even just from the vertex. So one of our vertices, just coming from our absolute value function, is 1, -3. Our other one we can pretty clearly identify crossing here is 4, 0. It looks like we have another one crossing at -4, 2. And another one at -4, looks like 4. Now let's go ahead though and algebraically prove that this green one, in fact, no, I'm sorry, let's go ahead and actually prove the absolute value one, a little bit of a harder one. Let's go ahead and prove that this point right here, -4, 2, is actually crossing at -4, 2, dealing with the absolute value, that red, and the blue. So again, our absolute value was y is equal to absolute value of x minus 1 minus 3. And then our blue was x is equal to -4. Again, just looking at the red one and the blue one, this intersection right here. Kind of just confirming that this vertex is in fact what we think, -4, 2. Well, we know x is -4, so we can take that, throw it into our other function using the substitution method. So when we do that, we have y is equal to the absolute value of -4 minus 1, and then minus 3. Y then is equal to the absolute value of -4 minus 1 comes out to be -5 minus 3. Absolute value of -5 comes out to be regular 5 minus 3. So then y is equal to just 2. So in fact, that vertex comes out to be -4, 2, just like we thought based off the graph. And if you wanted to find this vertex, the green and the blue, you would just basically do the same thing, only you'd be using the blue equation and the green equation. All right, but it should come out to be -4, 4. Again, though, that is example 7 from our 3.3 set of notes.